Swayam Prabha. Digital India. Educated India.
Good morning. Welcome to week 6 of this ongoing online course on understanding and reducing GHG emissions. We are focusing on scope 1 and 2 emission reduction through building design and construction. This is first lecture of this week, and in this week we are going to talk about thermal comfort in building. Before I go to start talking about thermal comfort in building, and this is going to be a brief overview, let us quickly look at what we did in the previous week. So, we looked at the scope 1, 2 and 3 emissions of different sectors of companies. We looked at airports, university campuses, oil and gas companies, tech companies and real estate companies. For understanding their scope 1, 2 and 3 emissions, we looked at some of the case studies. So, we looked at Mumbai International Airport Limited, which is an exemplary case study as far as the efficiency and reduction of emissions is concerned. Then we looked at BITS Pilani campus, we looked at Shell group of companies, we looked at Microsoft and Mahindra Lifespaces Developer Limited. When we saw their scope 1, 2 and 3 emissions, we actually looked at the numbers as given in their publicly available audited and reported reports. So, these case studies were actually through the commitments and also the audited reports that these companies have provided in public forum. So, this is what we understood. Now, also when we were discussing about each of these different types of companies and sectors, we saw that building design and construction plays a significant role in reducing the GHG emissions, one towards emissions and also towards reducing the GHG emissions, and there is a wide scope of doing so. Another thing that we understood as a takeaway from this entire discussion was that the primary role of buildings is to provide comfort, thermal comfort, visual comfort, acoustic comfort, and for these different variety of functions that we saw, whether it is an airport building or a university campus or a tech company or anything, the primary purpose of buildings is to reduce the extremity of the climate, of the weather around, and to provide a comfortable environment inside. And in that process of doing so, of providing a comfortable environment, a lot of energy is consumed during the operations of the building. So, at the end of the day, we are talking about providing comfort. Now, in this particular lecture, we are going to talk about thermal comfort first. There is going to be other dimensions, visual comfort, acoustic comfort we are not going to cover as part of this course, but we will very briefly understand the visual comfort and how it is ensured and how we can reduce energy consumption and emissions through that. But here we are going to quickly understand about thermal comfort. What are the factors which affect thermal comfort, the thermal comfort, thermal indoor environment, and we will look at not really thermal comfort indices, but we will understand that how thermal comfort can be created and understood as a concept. So, quickly if we look at the definition of thermal comfort, it is the condition of mind which expresses satisfaction with the thermal environment, because there are large variations both physiologically and psychologically. From person to person, it is difficult to satisfy everyone in a space. Now, it is basically the absence of irritation or discomfort due to heat or cold is what we know as thermal comfort. Very simply, if I am comfortable right now, if my body does not need to exchange with the environment, the heat or coolth to maintain its comfort, that is when I will say that I am thermally comfortable. Now, how would we know that it is thermally comfortable? As we just saw that from person to person the perception will vary. So, the scientists have worked towards it and they have developed something called thermal comfort indices, thermal comfort index, and there they have kind of devised kind of a scale, multiple different types of scales to record how many people are feeling comfortable in the environment right now. So, some are perception based scale like Likert, simple scales where if we are comfortable, we will say we are neutral, if we are feeling warm, hot or not or cold or slightly cold. So, this is the range, this is the kind of scale that we have. There are also indices where we know exactly what affects thermal comfort and we know the quantitative value. So, we know the temperature value, we know the relative humidity value and other factors which impact thermal comfort, and we calculate it to arrive at a thermal comfort number. So, these are indices, different indices are there. When we say that it varies from person to person, so it cannot be a fixed value. For a long time we had a fixed value. Okay, this is the range of thermal comfort. Now, we also understand that the perception of thermal comfort or how comfortable do we feel in a given set of conditions varies from geographic region to region. This is dependent upon adaptability. So, if we are living in India, we are relatively more comfortable at higher temperatures, at warmer temperatures as compared to somebody living in Scandinavian countries or Nordic countries where the average temperatures are much lower. So, people adapt to the conditions around them, the environmental conditions around them, and that is what is exactly this adaptive thermal comfort tells us. So, it varies, the comfortable zone, the comfort zone varies for region to region, and this different countries have their own adaptive thermal comfort model, where we see that how the comfort zone is shifting. It can also be a seasonal shifting. So, since in India we are used to living, especially in residential areas, we are used to living in unconditioned areas. We do not condition our areas as the developed countries, the citizens in developed countries do. So, we are more comfortable even at higher temperatures and also at lower temperatures, and we adapt ourselves with clothing, with food, with activities. So, this is all part of adaptive thermal comfort. Now, coming to thermal comfort in buildings. So, basically thermal comfort describes the human satisfactory perception of the thermal environment, and when we are talking about the buildings, we are talking about a lot of different parameters and factors which will contribute to the perception of thermal comfort. So, what are these factors which affect thermal comfort? As per ASHRAE, there are two categories of factors. One is environmental factor, which is airspeed, relative humidity and radiant temperature. We will come to each of these factors, but primarily we are talking about the temperature, we are talking about the humidity and also the movement of air. Then we are talking about personal factors which are clothing insulation. So, how much clothing are we putting on, because it provides us an insulation, and we know it simply, we have seen when we feel hot. So, we provide less of clothing on our body because it provides lesser insulation. So, it allows heat to be dissipated faster. And the second one is metabolic rate. So, we will come to all these factors one by one, but these are the 5 primary factors. So, if we are talking about environmental factors, first one is the temperature, the air temperature. So, it is the average temperature of the air that the occupant is surrounded with. We have two temperatures. One is a dry bulb temperature, which is read on a regular thermometer. So, now this is not taking into account the effect of radiation or humidity that is present around. The second one is wet bulb temperature, which is the temperature which takes into account the evaporative cooling effect, which is reduced due to the presence of excessive moisture. So, we have dry bulb temperature DBT and we also have WBT. So, both are measured using thermometers, but different types of thermometers. Radiant temperature is, if I simply explain to you, it is the temperature at which the body radiates heat at the same pace, at the same rate as it is in a black body with a constant temperature. So, basically what we are talking about is, for example, we have a room, a person sitting in a room, which is this actual room. So, we have different surfaces, we have a roof, we have a wall, we have a window, there might be radiation falling directly, there might be some equipment which might be producing heat. Now, the human body is responding to all these radiations which are due to different temperatures of these surrounding bodies, but the human body is radiating at a rate which is R. Now, if it is extremely difficult, it is a complex scenario, if we simplify it and we say that this human body, which is the same, is radiating at a rate R dash, and all these surfaces around are at the same temperature, which can be the integration of all of them, and the resultant R and R dash remain the same. So, R dash is same as R. So, this is the radiant temperature that we are talking about. So, mean radiant temperature is another factor that we talk about. And then relative humidity. Clearly, we understand relative humidity as the ratio of partial pressure or density of the water vapor in the air to the saturation pressure or density of water vapor at the same temperature and same total pressure. So, basically what we are talking about is when we have a higher relative humidity, which means the saturation level is higher, the capacity of air to absorb moisture or to take heat reduces. And when the air is drier, when there is lesser amount of vapor, water vapor present in it, it has a greater capacity to take moisture, to evaporate moisture, and thereby taking away the heat. So, this is the capacity that we are talking about when we say relative humidity. Now, coming to personal factors, we have a lot of internal processes that are going on in our body. We have evaporation, convection, perspiration is there. The body thermoregulates itself. So, there are internal processes such as vasodilation or vasoconstriction which are happening inside the body, but to be accounted for in the thermal comfort equations and the understanding of it, we are primarily looking at two factors. One is clothing insulation. So, higher is the amount of clothing that we put on, higher is the insulation due to clothing, and it is expressed in a unit called clo. So, if you can see here, the clo value is increasing from 0.5 here, from a very lightly dressed cotton clothes to heavy winter clothing. So, this insulation is increasing, this clo value is increasing, and there are charts, there are numbers which are available for the clothing that we put on and the corresponding insulation value in clo values. So, the naked body is considered to be having a 0 insulation because there is no insulation which is provided, and then the heavy business suit and heavy winter clothing. So, that has a higher value. Then the second thing is metabolic rate. Our metabolic rate is dependent upon again a lot of factors. As I said, there are personal factors inside each human body, and it varies from person to person, but largely what we understand is that it depends a lot on the activity that we are performing. So, it depends a lot on the activity that the body is performing. So, we generate less amount of heat. When we say metabolic rate, it is the rate at which the body produces heat. So, when we are sleeping, when our body is in a resting mode and there is no external activity being performed, but only the internal processes, at that time also the body generates heat. But compare it with very heavy, high intensity activity, for example, wrestling or playing basketball or a very fast game, or working, for example, intense working like carpentry or sewing. So, the metabolic rate increases, we perspire internally, the body also processes. So, if we are running, then the body perspires, there is perspiration that is happening, and that we clearly understand that there is a high amount of heat that is being produced due to metabolism. So, metabolic rate is again a personal factor that is accounted for in the when we are trying to understand thermal comfort in buildings. Now, once we have understood all these environmental and personal factors, then we have to see that these are not the only factors which are going to affect the indoor environment. There are interactions with the external environment that are going to take place. So, primarily there are three processes in which the heat exchange between the human body and its environment occurs, and this environment, which is the indoor environment, and the outdoor environment will occur. So, we primarily have radiation, convection and evaporation. So, conduction is when the heat is directly transmitted. So, these are simple processes, I am not going to go in detail over it, that we are talking about the heat exchange due to two different materials coming in contact, that is conduction. The second one is convection, when we know that it is due to the movement of particles, and primarily when we are focusing on building, when we say convection, we are talking about ventilation, the movement of air. The convection is happening. When the movement of air happens, convection happens, and that is how the heat exchange takes place. Every time I say heat exchange, it could be heat gain or heat loss. So, when we are talking about warm tropical countries like India, we are primarily concerned with heat gain, because the outdoor temperature is often higher than the required comfort temperatures. When we are talking about, for example, the extremely cold countries like the extreme northern parts or the extreme southern parts of the world, we are primarily talking about heat loss, because the average outdoor environmental temperature is lesser than the comfort temperature that we require. So, this is convection. Then evaporation is the process, again it is a heat exchange process where the state is changing from liquid to a gaseous state. So, evaporation of water is often the activity that we are going to concern ourselves with when we are looking at thermal comfort in buildings. And the last one is radiation, which is extremely important, because the buildings get heated primarily due to the heat received from sun, the solar radiation. So, sun brings in a lot of heat. Now, in certain scenarios, for example, the warm tropical climate, we will not need to bring in all that radiation inside, but that is again not throughout the year. In extreme winters, we may want to bring sun inside, and in extreme summers, we may want to cut off this solar radiation. While in extremely cold countries, we may want sun throughout the year to be brought inside. Now, how do we do that is what we have to understand. These processes, these fundamentals only tell us that what all is possible, but what we have to now see further ahead is how do we really achieve the thermal comfort inside the building through design as well as construction. Now, if we look at the sources, both internal and external, the heat sources and sources of cold. So, then we see that in the building, as I have just said, solar radiation is the primary source of heat for buildings. In addition to that, we have different equipments and appliances which produce heat. We get heat from the light, artificial lighting, because all luminaries, they have a fraction of this energy which is also converted into heat besides the light that it gives us. So, we have lighting fixtures, we have equipment such as computers, we have many other equipments that are going to be inside the building, and they produce heat, they add heat into the building. This is process heat. And then we also have human presence. So, we just have seen the metabolic rate. So, if there are only a few people sitting in the room, say 4 or 5, then the amount of heat that they add into the environment is lower, and compare it with 100 people sitting in one room, suddenly the room becomes very hot. We are not even talking about the carbon dioxide that is exhaled by the people, but we are primarily talking about the heat that is released into the environment. So, when it is extremely cold, we tend to huddle together. Animals in general, you would see that when it is extremely cold, they would come very close to each other, because they are giving heat to each other, and they are also conserving heat by reducing the surface area. So, all this thing we are going to see further, but these are the common sources of heat that we have to tackle. And if we are talking about cold countries, we are talking about these sources of cold. So, we are talking about different surfaces, not just window surfaces, but all the surfaces of this building which can exchange heat due to conduction or radiation. any body which is at a higher temperature will radiate heat to the to another body or environment which is at a lower temperature. So, we are talking about all surfaces, window surfaces, wall surfaces, roof surfaces, and to reduce that we may be needing to have insulation provided, so that less heat exchange is happening through different processes. Then we are also talking about the leaks and bridges, thermal bridges in the constructions, which are the common sources of heat loss in buildings. Now, all these sources, whether they are of heat or cold, they have to be tackled when we are designing buildings if we want to reduce the energy consumption. This is something that we have to understand, that how this whole understanding of thermal comfort is translated into GHG emissions. Now, if there is less comfort which is inside the building, or the building is not comfortable, then what will I need to do today? We will add air conditioning, or we will add fans, or we will add artificial lighting. In case of thermal comfort, we will add HVAC, whether we will heat the building, or we will ventilate the building, or we will cool the building. Either of the three processes will be happening there mechanically, and when we have to do all that mechanically, then we will be adding electricity, or we will be consuming electricity to extract the heat out of the building or to provide heat into the building. Now, this thermal comfort is directly translating into energy consumption, and the moment we see that the building needs electricity to maintain comfort, we are directly talking about scope 2 emissions. Now, this link has to be directly clear. If the building is comfortable, there is less of scope 2 emission, GHG emission, that is going to be there. Less energy consumption, less GHG emission. And so, what we need to do is we need to reduce the amount of energy that is required for conditioning the environment and make it passively cooled. The other thing that we can also do is personal factors. Now, activity we cannot control, because if it is an office building and people tend to sit on their seats for a long time, their metabolic rates are going to be lower. The amount of heat that they produce are going to be lower. In extreme cold climates, in extreme cold season, we cannot ask people to start indulging in high intensity activities. We cannot ask them to start running and jogging around. That is not possible. So, the activity part is separate. There is no impact on it. But what we can influence through behavioral change and the requirements is the acceptance of kind of clothing that they put on. For example, in corporate offices, the commonly accepted attire even in extreme summers is a coat, a blazer. Now, it adds a lot of insulation to the human body, and if you have to put on a blazer or a coat, we will need to add extra electricity, extra cooling into the space, because the metabolic rate is going to be higher. There is more amount of cooling that is required to keep the person comfortable. So, these behavioral changes can also make the requirement as lesser and eventually the GHG emissions. Another thing that we have to understand about this whole process or different processes by which heat exchange takes place is the capacity of this hard surface, most of the materials of which the building is constructed, the capacity of them to absorb heat and then to re-radiate it at a later time. Now, this is where we are talking about short and long wave radiations. Now, short wave radiations are the radiations that are received from sun. They travel a long distance, they are largely the visible light that we understand. So, this is the direct solar radiation that is received from sun to earth, different objects. Now, when different objects absorb them and when they re-radiate them, because it is not that high energy, so that is the long wave radiation. Now, it is the re-radiated energy most of the time that we are talking about. Now, what happens is that certain materials, the hard materials, they have a higher capacity to absorb heat. So, they will absorb a lot of heat during the day when the sun is there, when solar radiation is falling on them. And when the outdoor temperature falls below the surface temperature of this body, for example, a wall, a stone wall. Now, this stone wall will absorb a lot of heat during the day and it will re-radiate it during the night when the outdoor air temperature is lower and this stone body is at a higher temperature. So, it re-radiates it back. Now, if there is a body which is thinner, it does not absorb much heat or its surface temperature increases quickly, then it will be radiating it faster inside. So, these are the fundamentals. So, the specific heat of the material, the heat capacity of the material is to be understood when we are selecting the material for a specific climate. So, these are the fundamentals that we need to know before we design the buildings. However, since we are focusing on GHG emissions primarily in this course, I am not going to go in detail over it, but these are some topics that you need to read before we go ahead and understand the passive design of buildings and what strategies can be employed to really understand what is happening. Now, before we go on to understand or to read about the passive design strategies, one quick thing that we will do here is understanding the psychrometric chart. Now, psychrometric chart is putting all these environmental factors onto one chart. So, we are talking about the dry bulb temperature, we are talking about the moisture content and we are talking about the relative humidity. So, these lines they tell us about the relative humidity here. Now, together taking all of them together, the comfort zone has been arrived at. So, it could be by taking the definition of adaptive thermal comfort or the thermal comfort alone, but if this is the comfort zone that has been arrived. So, this is naturally occurring. What are the strategies by which we can expand the comfort zone? So, if you look at this here, this is the dry bulb temperature increasing and this is the moisture content increasing, which means that the humidity is going on increasing like this here. So, understand this, if we have low humidity, we are talking about low humidity here and higher temperatures, when the temperatures are higher and the humidity is lower, all we need to do is provide for evaporative cooling. And that is what you would have seen, that in extremely hot dry climates, smaller pools of water or sprays of water are used to create comfortable environment inside, or even the desert cooler, it draws its name, from the fact that it actually works in a desert like climate. So, that is where the evaporative cooling is happening and that is quite effective when we have the condition where the temperatures are higher and the humidity is lower. We will not need much of energy if we have evaporative cooling passively done in the building for this entire zone. So, which this entire zone that you see as EC is where we will have only evaporative cooling required. Now, if we have temperatures which are higher, slightly higher than comfort, but moderate humidity, not very high humidity, but moderate humidity, we are talking about around 40 to 50% of relative humidity, that can be handled with provision of high mass and high mass plus night ventilation, which is precisely what we might have seen in a lot of traditional residential buildings, havelis of hot dry region like Rajasthan or even composite climate like the northern part of the country, where thick walls, very thick walls will be provided, which will absorb a lot of heat and re-radiate it back without re-radiating it inside. If it is further higher a temperature, then we will need night ventilation. So, in the night that the air temperature will be lower and we will allow for night ventilation to take away the heat that is radiated or captured inside the building. If it is further higher humidity, not very high temperature, still higher but not extremely high temperatures, then all we need is to provide for natural ventilation. We are talking about warm humid areas here, for example, the coastal areas. In the coastal areas, the temperatures would range between 30, 35, 25 to 35 throughout the year. We do not need cooling there, we need ventilation, because the humidity is high, evaporative cooling does not work, it is only air speed, the movement of air, which provides comfort. So, this is what we have to understand when we are designing building. So, understanding how thermal comfort will be brought, what all will cause, and what numbers do we need to achieve to feel thermally comfortable, we need to know that. We need to understand the processes that are going to take place between the indoor and outdoor of the building, between the human body and indoor of the building. So, we need to understand those processes, and then we also need to understand that how to respond to each of these situations when we are talking about the design, passive design of buildings. So, with this understanding, I will stop here. I will close my lecture, and we will move on. We will look at different passive design strategies in the next lecture, so that we understand how to design buildings which will have lesser energy requirement to create thermal comfort. Thank you very much for joining me today. See you in the next lecture tomorrow. Bye bye.